So hello, welcome everyone, and thank you for coming. I know it's getting late in the afternoon on the second day of the conference, so thanks for sticking around. My name is Nick Pinkernell, and I'm a senior researcher at Comcast with Comcast Applied AI. So what our team does is works on models not only from classical models, but all the way up to deep learning models for our computer vision, our natural language processing. And what I'll show you today is some of how we get those models from the researchers all the way to production using Kubernetes. So as you might have heard from the keynote from Jan Neumann and Jim Forsyth, we invoke models billions of times per day, and we need a fairly robust way to do that. So some of the things I'll be covering today are, as you can see up there, why might you care? Why might you be interested in hearing all of this? Well, you might be interested in model serving, maybe a little bit differently than you've seen it earlier in the talk, with MLflow serving or with other tools. You might be interested in Kubernetes, or you may just be interested in hearing a little more about how what we do at scale. So some of the challenges and motivations. Comcast is a large organization, and all over the org we have multiple data science teams working on varied projects. In particular, some of the projects I was working on in the past, there were a number of challenges, and some of those challenges were we didn't have any model management or tracking, and we also didn't have standardized ways to package our models and to get them into production, to version them, a number of other things. Some of the other challenges we had were that there was code rewrite between the research folks and the operations folks, and that is incredibly error prone if anybody's ever played the game Telephone. You know, taking Python code and converting it to Scala or Java or whatnot for operational use, for something more performant. It's quite a time-consuming process. So the last thing is it really fostered some poor behavior. And what ended up happening was over a few months of this slow deployment process, our researchers learned that if they simplified their models, they could get them into production much quicker. If they just used classical models or if they used simple coefficients, for those sorts of things, they could get them out rapidly versus some of our more advanced models like neural nets and TensorFlow models. So with the challenges, we also had to come up with a list of core requirements that we wanted this architecture to satisfy. Some of that obviously was to remove the code refactorization between research and operations. We also wanted easier ways to experiment and track those, to package our models. We wanted researchers to actually deploy their own models after they wrote the code and had committed it to Git. We wanted A/B testing. We also wanted the ability to modularize any piece of the call stack or the call flow, and so we could inject custom metrics and do a number of other things within that flow. So what we chose was the following technologies. There are hundreds of technologies out there to use nowadays for various components. There's Acumos, SageMaker, BigHead, Clipper, so many things that out there to use. This is what we settled on, and here's why. For the research stack, we wanted it to be simple. We wanted our researchers to just be able to write their code, train their models, and to be able to do that on massive data sets. We don't want just subsamples or small data sets. We want them to be able to work on the entire data sets that we have in S3. So with that, they use DataBricks notebooks, they use Spark in the back end, and then to package and track the particular models, they use MLflow. We use Docker to contain everything, and then for our entire CI/CD pipeline and for our deployment process, we use Kubernetes, and more specifically, we use Kubeflow and Selden core. How many people are familiar with Selden core here? Okay, not many. So if you haven't looked at their documentation or their project, it's fantastic, and it's fully integrated with Kubeflow. I'll be showing more of that later. But with these technologies, how do we look at our pipeline end to end, and how do we abstract that? Well, we have our motivations and challenges, we have our requirements, and now we need to determine our particular use cases of how these models are going to get invoked at scale. So what we need to do is identify some of the commonalities, abstract those interfaces, and ensure those contracts between components are standard, and then automate every piece. So we came up with two simple use cases that would satisfy the majority of what we were wanting to do in terms of invoking these models at the end. These two use cases are the on-demand piece, which covers users clicking on things, and then the streaming use case is telemetry and a number of other automated stream data that we get in. So this enabled us to think about the components and choose what was common between those two use cases. This improves code reuse, and we can also leverage Docker layers for similarities within the images, those sorts of things. So now that we have those laid out, that on-demand use case, we can dig in that to a little, into that just a little more, and we can determine the customers or users who are on our mobile apps, our phone and voice search systems, other back-end systems that are more reactionary, like the systems that want to invoke callbacks or are just ad hoc, not scheduled. For that streaming action, we get gigabytes and terabytes of telemetry from our customer premise equipment every day. We get errors and events about what folks are viewing so that we can improve those. We have errors from our back office systems and actions from those systems, provisioning, billing. We receive a tremendous amount of data in our streaming use case. With that, though, we do need to store a few things. And we looked at a number of different technologies for this feature store. It had to be quick. We didn't really care about the consistency, about the availability here, because most of these things are fairly available now. But we did care about consistency and performance from the CAP theorem, right? So what we ended up with choosing for our feature store was Redis. And the reason we chose that is because we can do simple operations back and forth. We can save the last value that came in from our streaming use case, or the last user action and some of the payloads from a particular click or a tap on a mobile application. And we cache those. In that Redis, we also have custom code to perform windowing and aggregations and filtering functions. But most of that was fairly manual. Moving on, we can now lay out two pieces, which I'm sure you all have seen from many other talks or the keynotes or just that ML lifecycle diagram that's pretty common. We need to consume and parse the data. And not shown here, we're actually working on a standardized mechanism for metadata handling so that contracts can be strictly typed and predefined so we can continue our automation there. Once that JSON has been parsed, or our protobuffer Avro, and that's been turned into features, then we obviously need to perform normalization or transformation on those data sets. And that normalization, the nice thing here is that we can abstract it because it's a common piece, and then that can be reused. So, and everybody knows, transforming, one-hot encoding, those sorts of things. The final piece is invoking the model. And the model invocation actually changes whether it's a user action or whether it's a streaming action in terms of the response. Once the model gets invoked, if it was a user action, the user will get a callback from that model through various other systems, and then they'll get the inference or prediction or output from that particular model or ensemble models. And then for our streaming use case, we stream that up through the upstream systems, which we have defined in our graphs, or we persist it off to S3. And there's a number of other things we do in between each of these pieces for storing metrics so we can enable distributed tracing. If we look at these three components and really separate those out, we can begin to think about them in a more abstract way. And if we think back to our requirements, we can increase refactoring for reuse. We can reduce code rewrite for a number of these very common things. And we can also think about them how they would be implemented in our target architecture, which very naturally lends itself to Kubernetes pods. So here we have just a natural sort of transition of thinking about these components and their modularity, and then converting them into something a little bit more concrete. So when we look at the consume and parse pods, these could be things as simple as Kafka consumers or Kinesis consumers. These could be custom listeners that you implement. These, they could be a number of other things, such as enrichment or pre-processing steps before you pass them to your transformation and normalization piece. For the transformation and normalization pods, we can reduce these down to things that are used every day, such as the one-hot encoding, the vectorization, label binarization, TF-IDF weighting, many others, dictionary encoding. So those things can pretty much just become standardized. We include them in our call graphs, and you'll see that a bit later. The last bit here is for model invocation. And Selden core does something very nice for us, which it lives in Kubeflow. It has a model orchestration piece at the top there, and that pod has a standardized API contract for both REST and gRPC. When that gets a request in, or a batch of requests, it then invokes all of the components within its graph. And those components within the graph will return up through however the graph was constructed, and then back to the model orchestration piece, and back to the requester. So breaking these down also allows us to take particular models and perform A/B testing on them, multi-arm bandits for our other pods, and other combinations. This is an example of a Selden inference graph as it's actually generated from the Python code. If you look at their advanced graphs in their 0.2 release, you can generate these programmatically in your Jupyter notebooks or your Python notebooks. So this particular graph actually shows an ensemble model with 3 classifiers. And the way it builds its graphs are a little bit backwards if you think about them that way, because each of those classifiers has a REST endpoint, but the ensemble endpoint also has a REST endpoint. So it's laid out a little strange the way they draw their graphs, but you get used to it. What this allows us to do is not conform ourselves to a particular set of predefined templates for our models. We can develop graphs as simple as a single classifier, or we can develop models that have hundreds of neural networks behind that call graph. So that's all well and good, right? But we need a way to package and track our runs and our experiments and our models through various testing of hyperparameters and tuning. So we didn't want to put too much time into this, mainly because MLflow has done it for us. And as I said before, our researchers code in DataBricks, and then we package and track with MLflow, and then we deploy everything with Kubeflow and Selden. So an MLflow experiment, I'm sure you've seen something similar earlier. What I have done is boiled it down to a particular single run. This example is just a run with no outliers and default hyperparameters. That first line is to train the model based on our training set with our solver and our hyperparameters. We next call the prediction function on this particular model. And you'll see later it's just the iris data set, kind of one of the hello worlds of these models here. We get our evaluation metrics, and then down below is the real specific piece that MLflow gives us, which is nice. And that's to be able to log our parameters and log our metrics between runs. That last line, second to last line, is actually very important. What it does is it persists that model artifact to disk, and then we're able to introspect that, figure out which one it is, and deploy that particular run to production. As you saw in the keynote earlier, they did it with one click with Azure. We do it a little bit more manual so that we can customize and control it. This is a simple example of 4 runs with that iris data set, and I introduced some pretty radical outliers into that data set to kind of skew the results. And what you can see is the metrics that I've added, the parameters, the hyperparameters, and then the particular labels for those runs. And using R² as the only measure, which is not terrible, but it's not the best. But it is one way to look at it. We chose the last one, which had modified hyperparameters and no outliers. So the predictions closely approximate the real data, a little bit better than those others, which are 0.88 and obviously much worse. So that nice piece about looking at the run ID is that run ID becomes important because it enables us in our automated pipelines to inject that into our classification code templates and then deploy this particular model from those set of experiments. Going back to the flow of how we do things, the researchers, again, write their code in DataBricks and Python, and then they also need to do something else if they want something more complex than what we have templates for. And that's they need to write their own YAML or JSON configuration files for the Selden core graph implementation. This code gets committed to Git, and then we use something called Argo CD, which lives in Kubeflow. And we use Argo CD to pick up changes in those YAML or JSON configuration files. If there's a change detected in Git, it will kick off an Argo CD workflow build, similar to Airflow, as you might have seen earlier in the keynote. And it constructs the Docker images, uploads those to our Docker hub, does the deploy in Kubernetes, and then pulls those images down. So we've really consolidated the flow here. There is one downside, and we actually turned lemons into lemonade, at least at a big organization. This code piece between DataBricks and Git, we had an issue with that. And because we run a lot of our own services and our own VPCs in AWS, we have a lot of our own special networking. DataBricks to our Comcast GitHub Enterprise repository doesn't work due to firewalls and ACLs. That was a huge issue for us. But we took that and we turned it into a positive. And what that positive allowed us to do was to automate this flow with some fairly simple code and do a number of things we otherwise wouldn't have been able to do. So with that, this is the flow it allowed us to do. So when we detect changes in the DataBricks notebooks, and we only run these like every hour to compute those deltas, essentially to look at the code. But if we determine changes, we first check, is this researcher's repository synced up with Argo? If it's not, we add that repository to the Argo configuration. If it is, then we try to determine those code changes, right? If those code changes involve an MLflow model, we will train that model. Otherwise, we'll just tag those changes. In either case, if it's not an MLflow model, like I said, we'll train it. And then once they're tagged, we will create or update the Argo app. So we'll create it if it didn't exist prior. And if it did exist, we will increment the version number for that deploy. We will record those changes in our Jira instances, as well as our Slack channels and a number of other notifications, and that will then get deployed to our development or staging environments. So this is all nice, but what about production? And what about rate limiting and a number of other things in terms of advanced HTTP and gRPC routing that we want to be able to do with models at scale? Well, to the rescue comes Ambassador. And what Ambassador does is it sits in front of that service orchestrator that I demonstrated earlier with Selden core. It sits in front of that service orchestrator, and it looks at all of the HTTP and gRPC requests coming in. It allows us to do a number of things. We can change the URL of the particular model. We can rate limit requests. We can scale based on the request rate or other custom metrics that are in those payloads or headers. It's fairly flexible. In terms of the scaling bit, we're actually still working on getting that right. However, we do look at throughput and a number of other things to right-size the number of replicas for our Kubernetes pods before we push it to production. But eventually that will be handled with Ambassador as well. So in terms of throughput, it's a little bit hard to see, but the nice thing is it's very performant, especially for simpler models. For some of the TensorFlow and more advanced models, it slows down a little bit, but then we just add more replicas. So the load that we saw with Selden core and Kubeflow and Kubernetes on a single node with a single replica of that particular model, we saw about 700 requests per second. Not too shabby. And it was on a machine with pretty poor specs. If you go to Selden Core's website, you can see the benchmarking they've done, and it's fairly impressive on Google Cloud. Our other clusters are much bigger, and we've seen upwards of 100,000 requests per second to some of our production models at burst. So it's definitely performant. We are also using Locust in part of our CI/CD pipelines. I didn't show that earlier, but we use Locust to perform some automatic load testing for predefined data sets. And I'll show some of those in the model in the demo as well. Excuse me. So here's the demo. What I'll show you is I will show you the actual code for the consumer, a producer from Kafka. I will show you the code for the Iris classifier, the YAML configuration, how you can deploy the model, and how we can actually simulate it and do a little bit of load testing. So I'll switch to that now. Here, if I can find the mouse. There it is, okay. So, all right. So what we'll do is we'll step through the classifier first. And the classifier code is incredibly simple, and it's wonderful. This is actually a template that we have, but I've renamed it Iris Classifier. And that particular run ID that I have highlighted there is that run ID that we got from that MLflow experiment run. We update this automatically with some of our processes, and this changes, the version gets incremented, and that's it. The model artifact is already built. So if we go back to MLflow here, and we look at, this is a little bit updated because I added accuracy for fun, but with no outliers, modified hyperparameters, good accuracy, good R squared here. We can look at that run ID, which is the run ID I've used, and if you drill down into the model artifact, you can see that this is a pickle file. So that pickle file pretty much encapsulates the logic for that classifier and converts it into a binary format that can be embedded within our Docker images. So if we go back to our classifier here, you can see that there's this predict method. And you might be asking, well, why implement the predict method? What's calling this predict method? Well, you can see that there are two parameters here that are passed in. There's an X, which is an M by N matrix of features, and then there's a single array of features. That's not my method, that's actually Selden Core's method. It's the method that you implement so that the Selden Core service orchestrator knows what to call. And to determine that, you define the contract here for the model name and the actual service type. That might be a little small. Can everybody see that? Okay, great. So with that model name and service type, we define that particular classifier. And we have the predict method. Selden also supports binary data as well as string blobs. So you could have binary large objects or string large objects. And we've leveraged that a little bit for some of our custom JSON payloads. But here I'm just using the standard tensor format. So that's all great. A very simple classifier that we've trained with MLflow. How do we get it to production? Well, it's a little tricky. And this is why we've automated so much of it. I don't know if you've heard of tools such as KSonnet or Helm, but what they allow you to do is generate Kubernetes YAML so that you don't have to hand code all of it, which is fairly cumbersome. In terms of some of our more advanced graphs, we do have to hand code those, but that's okay, they don't change too much. So when you look at the deployment descriptor here, the deployment configuration, for Selden, you can see that we have the Docker image defined. And this is just sklearn iris MLflow 0.3. If you had other images within your graph, you would define them there. And here below is where we define our graph. And this is where you would define the children and the children's children of that graph in your call flow. For example, in the image I showed earlier, you would have 4 total elements in this graph, 1 for the ensemble and 3 classifier images. So that's great. We have this JSON. How do we deploy that? Well, it's actually fairly simple. All we do is that command. But nobody really wants to run a kube control apply on a JSON or YAML file. That's why we have Argo CD do it for us. So once that's deployed, you can see that we have all these pods running locally. And if nobody has used Docker for Mac in terms of the Kubernetes piece of it, it's fantastic. So here, all namespaces. If I could type. Okay, there we go. So if you look at all of those pods, I've reduced the set of pods that are running locally just for memory purposes. But even this wouldn't be possible without this really nice piece over here, Kubernetes on Docker for Mac. What it allows you to do is run a Kubernetes cluster locally without running Minikube, because Minikube is fairly resource intensive. So I'm still able to run a number of the things I want to run within the Kubeflow stack, and I'm able to run my model, as well as another pod here. And this other pod is this Iris Kafka consumer, and that will help me simulate requests here that I'll show you in just a minute. So that's great. We have our model deployed. Now let's send some requests to it. We have this simple consumer, and this Kafka consumer is not doing anything horrendously special. It's looking at a host Docker internal so that we can connect to Kafka running from within Kubernetes to our Mac. and we're looking at this MNIST topic. This Selden core ambassador piece allows us to invoke the ambassador pod running in front of Selden core, and that's all from within Kubernetes. The reason we don't specify something more like an FQDN here is because kubedns handles that for us within Kubernetes. Once we get a message for the consumer, we build the actual Selden request here, and you can see that this object has a fairly simple format. It's a data JSON object with names, a tensor, a shape of the tensor, and the actual features for that. Right now, that's just a 1x4 array. So that's great. We can consume our data as part of our pipeline that we showed earlier, and we can send that to our model. Well, let's send some synthetic data to our model then. Here's the producer, equally simple. We define our local Kafka, load our Iris data set just as a way to simulate some of these requests to our model, and we will do these at 2 messages per second. So if we go back here I'm actually running Zookeeper, I'm running the Kafka daemon, I'm running a kube control proxy so that we can see our metrics, and I'm also running the MLflow instance. So if we kick off our producer here, and then we go over to our metrics, what we can see is nice operational metrics. And as you can see, that's currently both producing and consuming, and this should equalize or plateau around 2 requests per second, or exactly 2 requests per second. The nice thing here is both Kubeflow and Selden have given us introspection and Prometheus metrics at model serving. We can drill this down into a mean, which it hasn't collected enough data yet, or 95th and 99th percentile, those sorts of things. What this also allows us to do is we can add custom metrics to our models so that we can look at various parts of our call graph. Like in that advanced graph I showed, you could add metrics to each of those classifiers, and they could be different. We can add metrics to the service orchestrator and a number of other things. It's very flexible and allows us to scale these things up. Once that's plateauing here, then I will just show the last bit of how we actually do our scaling. And that scaling is really quite simple, because all we do is specify the number of replicas for the model that we want to run, and that's it. Built within our Argo CD pipelines, we can adjust these based on throughput or external configuration that we've specified from our previous load testing. And you can see, if you look at the pods, that's odd. Oh, wrong one. So you can see there are 2 particular components running for this very simple model. One of those, as I said earlier, is that Selden service orchestrator, and the other one is my Iris classifier. And with that, we have operational metrics. We've trained a model with MLflow. We've deployed it with Kubernetes and Kubeflow, and we also have operational metrics. And that's my talk. Thank you. Oh, any questions? Yeah, we have a couple minutes for questions. Go ahead. There's a mic right over there, or, yeah.
Please remember to rate this talk as well.
Thank you for the talk. So MLflow also offers a deployment capability to Kubernetes, whereas Selden also does the same. So what is the reason of going with Kubeflow and Selden instead of leveraging the MLflow deployment capability on Kubernetes?
Yeah, that's a good question. So the reason we went with Selden is because MLflow can handle a number of different model types, and Selden can handle a number of different model types. Selden gives us a little bit more ability to add custom metrics, to customize our call stacks, and those Selden advanced graphs are really appealing to us because we like to be able to build our own ensemble models.
Thanks. My question is probably the reverse of the previous one. When I look at the Kubeflow world in general, right, you can probably get most of the things here, right, from training to serving to the pipelines, right, using Kubeflow only, right? So is there a specific reason why you would need MLflow in this particular context?
For MLflow? Right. So we rely heavily on DataBricks, and we use that quite a bit. It's natural for us to use a standard package format, which MLflow gives us. We did look at using other package formats, but they were kind of all over the board. They were Pickle or PMML or TensorFlow serving. MLflow gives us one set of metadata and one standardized package format, so we can actually track those models.
By package format, you mean for the metadata part?
For the metadata?
You mean, because regardless of if you're using TensorFlow, you will get saved model format. If you're using PyTorch, you will get Pickle. Those are the native mechanisms. So I think you are saying for the metadata, you get one standardized mechanism.
Oh, correct. Yeah, if you go back to the, that's a good question. If you go back to MLflow, you'll see this standard metadata format with the model artifact. And you're right, that's primarily the reason we used it was because that metadata is standard for MLflow for various formats. Thank you.
Hi, thank you for an interesting talk. So my question is regarding your feature pipeline. So in general, for a lot of models, we see that it's not just you feed in a bunch of values, you generally have to do some sort of transformation. With TensorFlow saved model, for example, you could bake in your embedding tables and all of that so that you can just feed an input to the model, it works, right? How do you handle that in your cases? Like, where is the feature transformations baked in your model serving?
Where does the feature transformation take place?
Yeah, for inference, yeah.
Oh, for inference? Yeah, it's the same as the flow that we went over before. We've abstracted out the transformation and normalization pieces here within that. So we have standardized pods for particular types of transformations and normalizations that we can run.
Thank you.
Yep, thank you.
Thanks for the great talk also.
Thank you.
I have a question for how do you have a certain workflow when new data arise and you want to retrain your model? Is it like also automated or like you need to train the model in MLflow again manually and then you get the trained model and then you click and everything gets deployed to Kubeflow? Because earlier you said the trigger is actually the the push to Git, but
Correct, yeah. So right now, the researchers still have to run their experiment with MLflow. Even if it's just a single nightly job that's retraining the model based on temporal drift or something like that. So they still have to rerun that, or we schedule that. And then what happens is we schedule a Git commit as well with that version increment, and then that kicks off the rest of the flow. So there are two pieces to it. It's not fully automated yet, but we're working on it.
We have time for one more question.
Hi, thanks for a very nice talk. My question is about orchestration. So, like you are using Kubeflow. There are a number of orchestration tools out there. I just wanted to know, like, any particular things about your research, like how do you came to a conclusion to use Kubeflow? Like, what are the benefits you are getting it?
Okay, yeah, no, it's interesting. We looked at Airflow. We've obviously looked at Argo because it's within the Kubeflow ecosystem, and we've looked at a few other orchestration pieces. It gave us the most flexibility, and for Comcast, it's really specific and important for us to have flexibility because sometimes we're invoking models on various different networks over different virtual private connections within our AWS instances or on-prem. So it gives us that ability to call models and manually perform some of our ingest when we need to.
Let's thank Nick again, and please remember to rate his talk.
Thank you.